Hello, Bhavya.
Hello, Marco, and hello, everyone, and thank you so much for joining. Welcome to the webinar on how to determine the expected energy production for solar plants. We'll just wait a few more minutes, so if there's any other colleagues who are joining. And while we are waiting, let's just keep in mind some of the house rules that we'll be following. So if you have any questions throughout the presentation, please feel free to put them in the Q&A tab below. And if anything goes wrong or in case you get disconnected, please just refresh the browser and try joining again. And if you're interested in finding out more about us or the predictive analytics, there's a link in the chat below where you can book a demo with us. So yeah.
If Bhavya, you can please start sharing the screen also. Great. Yes.
Nice. Okay, then let's get started with the topic at our hand. But first, I'll just introduce myself. So I am Bhavya Dureja, and I'm working as a technical customer success manager now with 4+ years of experience at SmartHelio. And with me here, I have Dr. Marco Calizzi, who's our in-house technical expert, and will be talking about the more technical details about the topic. So over to you.
Thank you, Bhavya. It's a pleasure to be here. So I'm the senior data scientist at SmartHelio. I have a background with a PhD in physics, then transitioned over to data science, where I have more than 4 years experience in designing and developing algorithms for automated detection and prediction of faults in solar plants. So let me start with a joke. We always like to start our webinars with a joke. And this time, the problem is that expectations are too damn high. Everyone is suffering from this, but at the same time, everyone needs this. We cannot live without it. So in this webinar, we will try to understand why is it so important, but at the same time, why is it so difficult to use it accurately? So Bhavya, I'll let you introduce the topic.
Thanks, Marco. So for today's agenda, it'll be very direct. We'll just start with introducing who is SmartHelio. Then we'll deep dive right into the topic at our hand, expected energy production. We also have some real life case studies that we'll be discussing from our clients. And then we'll keep some of the time for the Q&A session at the end to answer all the questions that we'll be putting in the Q&A tab below. So let me start by introducing SmartHelio. So you know how when you're sick, you go to a doctor and he checks you up and fixes you? Exactly, that's what SmartHelio does. So we are the doctors for solar plants. We have a software which is autopilot, which can detect and predict faults in real-time basis. The aim is very simple here, is to help the asset managers prevent the downtime in the solar plants and to reduce the O&M costs. We are currently managing more than 6 gigawatt of solar portfolio with clients from all over the world. But the question is, how did it all start? So it started like almost now it's been 12 years of R&D that we've done. But when we started, our founders realized that there was a lack of labeled data in the solar PV industry. So that we realized the need for generating the label data, for which we ended up creating IoT sensors. These tiny sensors were connected to solar PV plants, and we were able to deploy thousands of them at different places in the world. With this data that we collected via these sensors, we were able to map the behavior of different faults that we see in the solar plants to the unique signatures in the IV curves. And on the basis of this, we ended up developing our algorithms, which can now not only classify faults, but also predict them. But where are we right now? So now the sensors are all one, and it's a software. It's a pure software solution that we have, which is called Autopilot. It's built on the foundation models and the algorithms that we created using this label data. And it's now, since it's pure software solution, it doesn't need any sensors, and it's platform and device agnostic. What that means is it can connect to whichever CMS portal that you're using, or whichever API, whichever inverter that is installed at your solar plant, or the SCADA systems in your assets. So now that was a lot of details. Now let's also see and talk about the audience here. So quiz time. So we would like to know, how do you calculate your expected energy for your solar plants? So there's a quiz on your screen right now. And okay, I see the answers coming in, and it's leaning towards.
I'm curious to see, honestly, what people do usually, because we have our own very specific way. Let's see.
As we have all the different answers, from simulation software to analysis to satellite data. Okay, let me just publish it now. And it's more on the expected side that, you know, most of the people use simulation softwares.
This is reassuring. Yeah, I like these results.
Okay.
But still some people are struggling with it.
Okay, so the next question for you is that what is the impact basically if let's say the expected energy calculation is wrong, which usually is, what do you think is the impact of that? Okay, we have all the different answers coming in. Yeah, it's actually interesting to see. Okay, we have a lot of all the above, which okay, let me share the results now. Okay. So yeah, we have more than almost 60% of the people marked it as all the above. So we know that, you know, this it has a lot of different impacts.
Yeah, this shows this is a really important topic. It's affecting all kind of sides of operations in a solar plant. Yeah.
Now, just one more question to understand the audience better. That whichever role matches your current position in the organization, to help understand the audience better. Okay, we have all the different people. We have a mix of everything. We have asset managers, we have performance analysts, we have senior management as well, and we have people from O&M, from the forecasting teams, and from other different teams. That is nice to know. Interesting. Okay, so thank you, and moving forward. So now let's dive right into the topic in our hand, which is the expected energy. So what's the definition? What is expected energy? So it's basically the energy that a plant should be producing given the weather conditions. But why is it so important? Because if you see, everything from contractual obligations to performance benchmarking to the financial forecasting, everything depends on the expected energy itself. But then here's the catch. There are just a lot of different factors that can affect your expected energy calculation and hence affect your performance and your revenues. So it's important to understand what exactly are the factors that are affecting the expected energy. So let's break down the topic and see how expected energy is calculated. And now, since things are getting more technical, I'll pass it over to my co-host Marco to take a lead here.
Thank you, Bhavya. So, as you said, expected energy is the energy that a plant should produce given the weather. And the definition is simple, and the theory is also simple initially. So you start from calculating the expected power at every timestamp for every input in your plant. And this expected power is defined by the rated power at standard conditions. This is given from the spec sheet of panel manufacturers and inverter manufacturers. At standard conditions means at 1,000 watts per square meter and 25 degrees Celsius. So you need also to divide on the right there by the 1,000 watts per square meter. But then you also need to factor in losses, unavoidable losses, like degradation, temperature, conversion and transmission of energy, as well as, and this is, we will see, a very key important factor, a correct estimation of the irradiance. After this is done, you can calculate the expected energy by simply integrating the power over time. In practice, this is done by summing up all the expected powers multiplied by their sampling period. The industry standard for the sampling period is 1 hour. We at SmartHelio can process any sampling period. The most common one, which is a good balance between computation load and accuracy, time resolution, is 5 minutes. We could have an entire webinar on this topic, and maybe we will in the future. But the key takeaway here is that you need to this product of time and power to get the energy for the desired time and at the desired level. You can have yearly energy, monthly, daily, at the inverter level, at the plant level, whatever you want. And then a third thing you need to compute is the performance ratio. We will talk extensively about this. Everyone always talks about the PR. PR is just the measured actual energy you produce divided by the expected energy, which is calculated as I just explained. But what are the most common errors that incur during the calculation of this expected energy? By far, in our experience, the main cause of errors is metadata errors. This means the information you have about your own assets. It could be a wrong orientation of the panels, a wrong knowledge about the structure of your array, number of strings in your array, or outdated information. Maybe you repowered and forgot to update the metadata. Maybe you replaced an inverter with different specs and you didn't update the metadata. Then the other big factor is irradiance issues. Everything depends on irradiance. This is solar energy, so it depends on the sun, and it's very important to measure it accurately. And uncalibrated or tilted POA sensors can cause all sorts of problems. We have also other kinds of factors that can create errors, which are incorrect loss parameters. It's important to accurately quantify permanent losses as shading, and as well as dynamic situations in the plant. I'm sorry, Bhavya, I lost your screen.
Sorry.
Yes.
Is it visible now?
Yeah, it's back on, thanks. As I was saying, dynamic plant conditions can also affect the calculation, and we will see this in our test cases later. But how do we deal with all these potential problems at SmartHelio? So we have developed our own weather service, which takes into account the on-site data, so the time series electrical production data, current and voltage, the system metadata, as well as the on-site time series irradiance data. And then we compare this with also third-party weather sources like satellite imagery, as well as clear sky models that we tune specifically for the site. We benchmark usually this clear sky model against nearby weather station in order to have the best possible precision for the site. And we combine then the clear sky model and the third-party sources to create a site adaptation that then is fed into machine learning model together with the client's on-site data to first filter out all the bad data points. What we want to have after this first model is to get only clear sky, non-faulty instances. And this is then used to compute weather correction to the weather data. And ultimately then, the output of this model is used to correct the weather data and use this instead in the ultimate calculation of the expected energy. So we will see how you apply this method in the various test cases that Bhavya will now introduce.
Thanks, Marco. So this particular case is coming from one of our utility scale solar developer in France, which has a portfolio of more than 1.5 gigawatt, and they have both CNI and ground mounted installation. It was a very peculiar case because the client noticed that even though the PR was high, it's, approximately 86%, but still the revenues in actual energy was decreasing. And there was a significant discrepancy between the actual and the expected energy. So, can you shed some light on here, Marco, that how did we help this client?
Definitely. So what we did is that we applied our weather service that I just explained, especially like the second and third step, where it is crucial to cross benchmark the on-site data, in this case, the irradiance sensor data from the client, with other sources. And by generating our simulation irradiance, we were able to see that there was a constant underestimation of irradiance by the customer's sensors. So, of course, a low irradiance translates into a low expected energy. But this went undetected because the actual measured energy output was also low. And this would kind of balance out to a decently high, artificially high PR. So you can see in the bar plot in the bottom right here, the green is the actual energy, and the yellow one is the client's expected energy, which is kind of close. It's 86%. But when we came in and corrected the expected energy, so if you replace the yellow with the blue, now you see a big difference. And by analyzing the shape of this discrepancy, so it was mostly constant with some slight variation depending on the time of the day, we suggested that the POA sensor of the client might be dusty and misaligned. And after they checked, indeed, this was the case. And this happened because simply they had no process for a periodic cleaning and calibration of sensors. It's something they didn't plan for, and it was affecting heavily their understanding of plant performance. So what was the impact of this finding? So the plant performance was lower than perceived, but they knew in the end from the concrete energy output and revenue gain that something was off. And thanks to our corrective action by cross-validating the irradiance, local irradiance data with the other sources, the Clear Sky model and the third-party weather sources, satellite imagery, we are able to assess that the real PR was 79%, so 7% lower. And this is where they understood that they had some real underperformance going on. And with our help, we continued solving their issue with our fault analytics. But the key takeaway here is that while PR is a very strong KPI, it is only as reliable as the data you use. And it's not enough to just rely for the irradiance on one sensor for your entire plant.
Interesting, Marco. Okay. Now so we have this another case study coming from one of our clients from Australia this time. They have quite a big plant of 130 megawatt with single axis trackers. And as compared to the previous case study where we just had a single sensor, here we had multiple sensors installed at the site. So there were 6 POA sensors with 3 GHI sensors as well. But what the client lagged here was the mapping between the sensors and the trackers. So the client did not know that which sensor exactly should be mapped to which of the inverters or trackers to accurately estimate the expected energy generation for the plant. So in the end, the approach that client took was that he ended up averaging the POA values across the site to estimate expected energy. But he knew that something was wrong because the values that he was getting did not make sense. But he could not pinpoint what exactly was the issue here. So, Marco, can you please explain how did we help help this client mask the underperformance, that was not clearly visible?
Yeah, sure. So yeah, indeed, this was a interesting and tricky case. There were several things going wrong. First of all, in this plant, some trackers were stuck under maintenance or just malfunctioning, and we identified this first of all by measuring the monthly average deviation from between the tracker position and their set point correct position. And you can see in this plot the tracker, the pixels that are darker are the trackers that are malfunctioning. And on some days, most of them were malfunctioning. This is because of some maintenance going on. So they were kept at the constant position. And then some others were just malfunctioning on their own. But since the POA sensors are moving with these trackers, the irradiance would also be wrong. And by averaging some good trackers irradiance with some malfunctioning irradiance coming from malfunctioning trackers, you mask this underperformance. And this was also confirmed from our clear sky and satellite data, showing significant differences compared to these sensors. And to make the things worse, these performance issues remained undetected for months, leading to inaccurate assessments. So what did we do at SmartHelio? First of all, we mapped the individual POA sensors to their respective trackers. This is possible to do by kind of normalizing the irradiance and the current coming from the various trackers. And they have to have the same shape. And then once this was done, we validated the sensor data using a POA transposed clear sky model, as well as satellite data and the GHI sensor transposed to the POA. So timestamp by timestamp, we would get the correct orientation of the tracker and transpose the GHI to that plane of array. And then this is the important step here. We identified then the best performing moments and used them as benchmark. So this is the purple line you see in the plot on the right is a collection after, of course, proper data filtration of moment by moment, the best irradiance values measured in the plant. And you can see this kind of squared off shape of the irradiance, which is typical for trackers, and indeed matches very well the blue line, which is the clear sky POA irradiance. Yeah. In red instead, you can see the irradiance data of some malfunctioning trackers. And you see here the trackers are initially following this purple curve, and then they are off. You see this typical bell-shaped curve for the red line. This means the tracker is stuck in one fixed position. And by recalibrating the expected energy model with our expected POA coming from the best performing moments, we were able to highlight at the tracker level this discrepancy between energy generated and expected energy. So this is how we were able to restore visibility into the underperformance, allowing the O&M for data-driven decisions and optimize plant operation, overall improving the efficiency and reducing energy losses, because you would react in timely to these problems. So in general, what is the SmartHelio approach to eliminating errors in the expected energy calculations? I hope I stress this fact enough, which is really the most important one, in my opinion. You need multi-source validation. So there is no one single source of truth. You need to combine your local POA sensors. This is great value, but you need also satellite data and adapted to your site clear sky models to validate, to be sure that all these data make sense together. And then you also need to do continuous benchmarking with the best input. You need a solid reference in your plant to be used for these estimations. And then another factor of expected energy is the quantification of unavoidable losses. And at SmartHelio, we can do this very efficiently thanks to our AI-powered models that can automatically and in real time detect degradation problems, shading, and also, as we'll see, all kinds of faults.
Thank you, Marco. And now coming to, after discussing about expected energy so much, I think there are just some key takeaways which are very simple to implement and that you can actually start implementing since tomorrow itself. So the first one would be definitely, as stressed by Marco enough already, that to validate the sensors data, both GHI and POA sensors, whichever are installed at your site, and should be validated either with the clear sky or satellite data. If can be done with both, that is amazing. But then you can do, at least you can start with one of the following, whichever is easily available with you. The next would be to use the customized expected energy models for each plant. So we have seen that there are always some site specific anomalies which are there to be accounted for each plant. So the expected energy model should be customized. Never trust the PR blindly, as was also the takeaway from the first case study that we had, because you can never trust the PR blindly. There are always other metrics that we have, such as energy yield and specific yield, that you can use, which tend to be more reliable. And then the last one is simple, but it's very important to keep a track of your metadata regularly, to know that whatever changes that you're making in your plant in terms of strings, connection, or the panels used should be maintained properly, and you have the plant's current structure available at any given point of time. So now it's quiz time again, but this time we're going to be testing your knowledge. So we have a list of faults that were detected by our software Autopilot, and now we'll be showing you those fault patterns, and you can make a guess if you're able to identify the fault. Okay, so you'll be shown 4 options along with the graph, and then you pick the one which you think is actually the fault being shown on the graph. So starting with the first one, so here is the graph. Please take 1 minute to understand what's happening here, and then I'll show you the answers. Okay, so now here are your options. So what do you think? Is this an inverter failure? Is this soiling, or just a low irradiance event, or a tracker malfunction? What is happening here? Okay, we have the answers coming in already. Okay, and it's a mix of everything. Okay. Okay, interesting. Okay, you have 5 more seconds to answer, and then I'll be closing this.
I'm curious to see what people answered. Let's see.
It's very interesting. Okay, we still have people answering. Okay, now I'm gonna close the poll. Okay, and yeah, I'm gonna be sharing the results. So we have tracker malfunction. So 40% of the people said tracker malfunction, but then we also have a good amount of people saying that it looked like an inverter failure or soiling. So let's see.
So the correct answer is tracker malfunction. Congrats to the one who guessed. So why is this? I can give a brief explanation. You can see in green and orange the current generated by some devices, and in dashed blue the irradiance. You can see most of the time the current has the same shape as the irradiance, but not in the morning. And this is when the trackers need to do the most work to follow the sun. And this is where some of them are not able to keep up. And you can see this is repeating day after day. So it's probably the motor that is struggling to move in a particular direction. And this is why the current in the morning cannot keep up with the irradiance.
Let's see the next quiz now. Okay, so the quiz, so this is the fault pattern, and yeah, I'll be giving you the options in another minute.
I'm sure our knowledgeable audience will mostly get this right. Let's see.
Okay, so I'm launching the options. And so what do you think? Is this a pattern for soiling or shading or power clipping, or is it disconnected strings? Okay. Okay. So we have most of the people. Okay. People are leaning towards one of the options here. So, okay. So you just have 5 more seconds to answer, and then I'll close the poll. Okay. Okay, I'm closing the poll now, and here are the results. So almost 80% of the people have said that this is power clipping.
Well done. Indeed, this is power clipping. This is a very typical signature. You can see the current, again, following the irradiance while the irradiance is low. But then when it reaches a certain threshold, the current plot just becomes flat. This is because you are being clipped by the grid. And some people might think this is a string disconnect. But while it's true, a string disconnect has lower current profile, but the shape is different. Here, it's very typical to see the current follows the irradiance, then becomes flat in the peak hours, while string disconnect is just overall factored lower. It's same shape, but lower intensity for the current. So again, congrats to all of our audience for getting this right. I was confident in you. Yeah.
Even though people who could not get the first 2 right, you still have 2 more chances. Okay, so this is the third quiz for you.
Mm-hmm.
That's quite interesting. Okay, so I'm gonna be launching the options now. And so what do you think? What this pattern shows? Is this bad or saturated values for irradiance, or is it module mismatch, DC cable loss, or cloud cover effect? So we already have answers coming in. Okay. And interesting. So we are again leaning towards one of the options here. So most of the people tend to think that this is a case of saturated values of irradiance.
Again, correct. Yes, this is indeed the case. You can understand that this is the case because you can see in blue the irradiance is very low for several continuous days, but at the same time you can see a reasonably shaped profile for the current and the voltage generation. So, of course, solar panels cannot produce current and voltage power without irradiance without the sun. So there must be something wrong with the irradiance sensor. And typically when there are saturated values, we get just all zeros or all nones or like 9,999. So again, this saturated values was the correct answers, and congrats to most of the audience again who guessed this right. I think with our LinkedIn posts, we are starting to educate, with these quizzes.
So last and the final quiz for the day, the pattern 4. So I'll be launching the poll. I'll be launching the options in 10 more seconds. Okay, so here are the options for this one. What do you think? Is this a pattern for degradation? Is this sensor calibration or disconnected strings, or is it grid curtailment?
I'm really curious to see the results on this one.
Same here.
Let's see.
Okay, we are still getting more answers. We are still filling up. Okay, and it's still again a mix of everything.
Yeah. This is what I expected, a bit of mix of everything. So why is that? Because this is actually a trick question. Also me, the first time I saw this pattern, I thought like, oh my God, what is happening? Because the data is good, it's just the irradiance is very unstable. It must be like a cloudy day. So this is a trick question because we didn't expect anyone to guess. And this shows why we need a software solution like Autopilot to detect that this is indeed degradation. Our algorithms are able to compute the expected energy and then the difference between with the actual energy at every timestamp and aggregate over time and see that there is a declining trend. So I hope people are a bit more convinced now about the usefulness and the power of our software.
So with this, the quiz is now over. And since we're almost at the end of this webinar, here's also another white paper that you can definitely have a look at, which is bridging the gap between the expected and the actual energy in solar plants. It has even more technical details that we discussed here today. The link for that you can find in the chat below. Okay. And lastly, since we are here, I would also like to take 2 minutes to introduce you, to show you our tool that our team has been recently working on, which is called the Fast Diagnostics tool. So this is similar to the Autopilot that our software, that we have the software, but it's a mini version of that. So it's, as the name suggests, it's a faster version of the Autopilot. Autopilot is a more heavy duty. So I'll just show you how it works. So let's say you have a plant, and this is a demo plant, which is approximately 2 years old, and it's located in Switzerland. So it's not happening. Okay, spellings are quite wrong, but okay. Then we add our inverter details here. So in this plant, we have 4 inverters. So I just select the inverters, then we put in the capacity. So this just needs very limited details. So the capacity that we're using here is 73. So all the inverters are of the same capacity. And then coincidentally, the efficiency is also the same for all the inverters, which is 98. So I select all these inverters, I submit the details, and then all I need to do now is to upload the time series data that we have, which is simply the power AC values for all the inverters. And yeah, this is how it looks like, and we do generate diagnostics. And in just a few minutes, this tool is able to diagnose whatever the issues are with your plant and exactly able to pinpoint where we need to focus upon. So yeah. So it's still loading. Okay, and here's the performance summary of the plan. So you have the key performance metrics. So we can already see that the plant is not performing very well. So the performance ratio is still below 60%. So that means there are a lot of issues with the plant itself. And if we move forward, it shows what was the quality of the data that provided, and most of it is green, so that means the data was good, with a little bit of red because there was missing values in all the inverters, but that is fine, it's not a lot. Then coming to the main thing, the loss distribution. So it shows how much we were expecting, so that is 100% of the expected energy, but the plant was only able to produce 53% of that. And then these are the major issues that the tool was able to detect. So there was inverter shutdown, inverter tripping happening. There was also some plant shutdowns that were detected. So yeah, so basically in just a few minutes, in less than 5 minutes, let's say, and you have the whole summary of how your plant is performing, and you're also able to identify where exactly the issue happened. And then it also gives you some recommendations. Like for power clipping, it detected that power clipping was happening in these two inverters. And then there's also recommendation that, what you should go and check at the plant so that you can take corrective actions for that. So yeah, so this is something that we have been working on. So yeah, now coming back to our presentation, let me just share my screen again. Just 1 second. So, Marco, can you please confirm if my screen is visible?
Yes, it is. Yeah,
so
it's Q&A time.
It's Q&A time, yes. So we have, and by the way, we have a lot of questions coming in already. So let's take this one. So one of the colleagues is asking, how do you consider P90?
Okay, I will take it. So P90 indicates that we wish for a 90% probability of exceedance level. So usually what we have described so far is to give the best expected energy value, which is P50. But this is often not desired by mostly investors. It's too risky. They want more of a safe bet. And we consider P90 by assessing. So if you remember the formula for the expected power is the rated power times the losses, the irradiance, and the irradiance and standard conditions. So by evaluating the best value as well as the error, we can assume a normal distribution of values with the standard deviation of the error with the mean of the expected value. And by composing then all these factors, we are able to produce the probability distribution of the expected energy. And then, given this, you can calculate the P90 or any other confidence interval, P50, P75, whatever you want.
Okay, and so thanks for answering that. Here's another one that we have. It's so the colleague is asking, what about curtailment? Do you include it in the expectation or not?
Yeah, this is a big topic. Also, in the fast diagnostic tool, you showed like most of the losses came from the curtailment. This is such a big issue for everyone. So this really depends. We quantify curtailment. So it's really up to the client if they want to consider it as a loss or factor it in the expected energy, so it shows because the thing is the curtailment is a loss that you cannot control. So by quantifying it, we just give the user, our customers, the ability to make decisions with it and use it however they want.
Thanks, Marco. So here's another one which is quite interesting. So let's take this one. So it says that parameter issue is big, and we are thinking to only use satellite data, but then satellite data is not optimized for the location always. Do you have some solution on this?
Yeah, sure. So I believe that having on-site irradiance measurements is a great added value, but I also understand the struggle. So I think I was able to convey by explaining our weather service how it is important to use also other sources, and it is indeed possible to calculate estimated expected energy without an on-site sensor. But I would advise against using the raw data coming from third-party weather sources. And this is why it is really important, especially if you don't have an on-site pyranometer. It is especially important to really fine-tune this data to your specific location and cross-benchmarking it with clear sky models.
We have other questions as well. So this is related to the tracker case study itself. So it says that I'm having issue with the expected energy calculation when I have POA on tracker, but sometimes tracker itself doesn't work and not performing. So do you have some tips?
Sorry, can you read again because I lost the question? How do your model incorporate the degradation of solar panel efficiency over time into expected energy calculation?
Yes, that's also one of them. Yes.
Okay. No, sorry, I missed. Where was it? Can you repeat the question, please? I was scrolling through other questions because there are so many that are
a lot of them, and I'm also a bit confused.
So I will take the one about degradation. I think it's interesting, and I am personally working on some degradation algorithm. So the degradation is a type of loss that is unavoidable, and we count it as an unavoidable loss. So it goes into lowering the final expected energy. And then how we calculate it. So you need, since it's a slow phenomenon, you usually need long-term data to precisely assess it. Usually you need at least 2 years of data to get the best results based on some year-over-year differences.
Thank you for that. So here's another one that we have.
I think we have time for one last question. Yeah.
Yes. So let's just take this one. So it says that I'm having issue with expected energy calculation when I have POA on tracker, but sometimes trackers itself doesn't work and not performing. Do you have some tips?
Yeah. So this is kind of related to our second case study. And it can be indeed tricky because if you rely only on your POA attached to your tracker, if the tracker is malfunctioning, you will not see it because it will measure the correct irradiance, but the angle is correct. And this is why it is important to take a step back and look at your plant as in its entirety. So you need to compare all of your trackers, all of your sensors together, and get the best one at every timestamp. And again, this always comes back, but this really is very important. Cross cross-reference these values with other sources.
Thank you, Marco. So we still have more questions, but we'll take them. We'll reply to them afterwards. But thank you so much for joining, everyone, and please don't forget to download our white paper. The link is in the chat below, and yeah, you will also receive an email from us with the webinar recording and the slides itself. So yeah, and thanks again for joining, and look forward to seeing you again.
You can show the link in the next slide.
Yes.
So people can scan the QR code.
Yes.
To reach out to us for more questions or demos.
Yeah, there's already a link for you if you want to know more, or if you have any more questions. There's already a link in the chat below to connect with us and for a demo, and we'll be very happy to answer all your questions. So, okay, then.
That's great. Thank you, everyone. Thank you, Bhavya, for hosting.
Thank you, Marco. Okay, then. Thank you.
See you next time.